Welcome to this detailed presentation on the waste-to-energy power generation system. Today, we are going to explore a cutting-edge technology that has the power to reshape how the world handles solid waste. Instead of allowing waste to sit in landfills, release harmful gases, and contaminate soil and water, this system transforms waste into a whole variety of extremely valuable resources. These include hydrogen, which is one of the cleanest fuels known today, freshwater, which is becoming more and more critical as water scarcity increases, electricity, which powers our homes and industries, oxygen, which has medical and industrial uses, and even hot air, which can be used in heating processes. This presentation will take you step by step through how the system works, why it is more efficient than traditional waste disposal technologies, and how advanced technologies like machine learning make it possible to maximize productivity while minimizing pollution. By the end of this video, you will not only understand the science behind this innovative waste-to-energy approach, but you will also see how technologies like these are essential for building a clean, sustainable future. Let's begin our journey towards turning waste into wealth. This slide gives us a clear overview of what the waste-to-energy power generation system actually accomplishes. Imagine a single facility that receives mixed municipal waste. This can include food waste, plastic bags, bottles, paper, rubber, textiles, and all sorts of everyday junk. Instead of dumping it into landfills, the system converts it into multiple high-value products. The first major product is hydrogen. Hydrogen is considered the fuel of the future because it produces zero emissions when used. It can run hydrogen vehicles, fuel cells, industrial furnaces, and even generate clean electricity. The second product is freshwater. With global water scarcity increasing, producing freshwater from waste heat is a major technological achievement. The third product is electricity, which is produced using advanced heat cycles. The fourth output is oxygen, which is valuable for medical, industrial, and chemical processes. And the fifth product is hot air, which can be used in industrial heating, drying processes, and space heating. What makes this system truly powerful is the use of machine learning. The system doesn't just operate blindly, it continuously monitors conditions and adjusts parameters to reach maximum efficiency. Machine learning models used in this study have an impressive accuracy of more than 99%. This means the system can predict performance, reduce emissions, and optimize output in real time. In summary, this slide shows that the power generation system is not just a waste treatment plant, it's a resource factory that turns garbage into multiple streams of wealth. This slide introduces the complete process flow of the power generation system. The system consists of 4 interconnected components working in harmony. Each stage supports the next, ensuring that no energy is wasted. The first stage is the combustion chamber, where solid waste is burned to release heat. Unlike conventional waste burners, this system is designed to capture and use nearly all the thermal energy created. The second stage is power generation using the supercritical co-Brayton cycle. This is one of the most advanced technologies in thermal power generation. The heat from combustion drives this system, allowing it to produce clean electricity efficiently. The third stage is the PEM electrolyzer, which uses the electricity from the previous stage to split water into hydrogen and oxygen. This is where hydrogen fuel is produced. The fourth stage is the HDH desalination unit. Instead of letting waste heat escape, the system uses this heat to convert seawater or brackish water into freshwater through humidification-dehumidification. Each stage feeds the next, creating a continuous loop where heat, electricity, and water interact to create multiple useful resources. This interconnected design greatly boosts efficiency and minimizes energy losses. The combustion chamber is the heart of the system where waste is transformed into thermal energy. The chamber burns waste at temperatures typically above 800 degrees Celsius. At this temperature, plastics, textile fibers, paper, and food waste all burn efficiently, producing high-temperature flue gases. The design of this chamber ensures complete combustion, meaning almost no unburned residue or harmful pollutants escape. The hot gases produced carry enormous energy, which is then transferred to the supercritical co-Brayton cycle. This is a major improvement over traditional incinerators, which waste most of their heat and produce high emissions. In this system, almost all the energy from waste is captured and utilized downstream. Furthermore, based on the chemical composition of the waste, equations are used to calculate how much oxygen is needed, how much CO will be produced, and how much heat will be released. Machine learning plays a role here too. By analyzing hundreds of combustion cycles, the system learns the best temperature and air supply required for maximum heat output with minimum emissions. This slide explains the supercritical CO-Brayton cycle in detail. The supercritical state of CO offers several advantages. It allows extremely efficient heat transfer, requires a smaller turbine, and operates smoothly at high pressure. In the cycle, CO enters a compressor, gets heated by combustion gases, expands through a turbine to generate power, and then is cooled again before re-entering the compressor. This closed-loop operation increases efficiency and reduces environmental impact. This system is more compact than steam power plants, requires less maintenance, and achieves higher output per unit of heat. Additionally, the lower operating temperature reduces material stress, increasing longevity. This slide emphasizes why modern energy systems are adopting supercritical CO cycles to replace older, This step turns everyday trash into the fuel that powers the entire system. The PEM electrolyzer plays a key role in producing hydrogen. PM stands for proton exchange membrane, a thin polymer membrane that conducts hydrogen ions. When electricity passes through the system, water molecules split into hydrogen at the cathode and oxygen at the anode. The membrane ensures that the gases do not mix, maintaining purity. Hydrogen produced in this way is extremely clean and has very high commercial value. It can be stored, transported, or used immediately in fuel cells. Oxygen, often overlooked, is also a useful byproduct, especially in medical, chemical, and industrial sectors. The HDH desalination unit is an excellent example of smart heat usage. Instead of letting waste heat escape into the environment, the system uses it to evaporate water. In the humidifier, warm seawater is sprayed or trickled over a heated surface, causing water vapor to form. This vapor is carried by air and then enters a cooling chamber, where it condenses into freshwater droplets. The process is simple, effective, and extremely energy efficient because it relies on heat that would otherwise be wasted. This technology is particularly valuable in regions facing water scarcity. It supports sustainable water production without relying on expensive electricity. This slide explains how waste heat becomes a life-saving resource, freshwater. Machine learning is the brain behind the operation. Using historical data, regression models were trained to predict system performance. These models take inputs like pressure ratio, temperature, waste feed rate, and calculate expected outputs, hydrogen production, power generation, freshwater yield, oxygen output, and emissions. What makes this impressive is the accuracy. R-squared values above 99% mean the model predictions are nearly identical to real-world results. This allows the system to be controlled automatically with minimal human intervention. Machine learning also monitors emissions and adjusts parameters in real time to stay within environmental limits. This reduces pollution, saves energy, and increases overall system reliability. This slide demonstrates how artificial intelligence enhances energy systems and makes them smarter and cleaner. His slide presents the key equation derived from machine learning that predicts hydrogen production. The inputs include pressure ratio, temperature, and waste feed rate. The analysis reveals that the waste feed rate has the highest impact on hydrogen production, contributing nearly 75% to the total output. Higher pressure ratios also increase hydrogen yields, while temperature adjustments fine-tune the performance. Understanding this equation allows operators to predict how much hydrogen will be produced based on how much waste is fed and under what operating conditions. The study identified the optimal operating conditions using machine learning. At a pressure ratio of 10.73 and a combustion temperature of around 863 degrees Celsius, the system achieves its best performance. Under these conditions, the overall efficiency reaches 69.62%, which is extremely high for a waste-to-energy system. Emissions are also remarkably low at 469.7 grams of CO per kilowatt-hour. This makes the system much cleaner than traditional waste disposal or fossil fuel power plants. These metrics prove that the system is both environmentally friendly and highly efficient. This slide explains how changing system parameters affects performance. Increasing the pressure ratio improves system efficiency and reduces emissions. This is because higher pressures allow better expansion in the turbine and more complete utilization of heat. On the other hand, lowering the combustion temperature also helps reduce emissions. Cooler combustion reduces the formation of nitrogen oxides and other pollutants. Machine learning helps identify the sweet spot between temperature and pressure to get maximum output with minimum emissions. This system is important for many reasons. First, it reduces landfill waste significantly. Instead of dumping garbage, this system uses it as fuel. Second, it produces clean hydrogen fuel and renewable electricity. These are essential for reducing dependence on fossil fuels and cutting carbon emissions. Third, it generates freshwater, a critical resource for millions of people around the world. Fourth, it uses machine learning to improve performance continuously. As the system runs longer, it becomes smarter and more efficient. Finally, it creates multiple revenue streams: hydrogen, water, power, oxygen, and heat, making the system economically attractive. This slide highlights how this technology can create both environmental and economic benefits. In conclusion, the waste-to-energy polygeneration system shows how a single integrated technology can turn solid waste into a wide range of valuable resources. By combining combustion, supercritical co-power generation, electrolysis, desalination, and machine learning, the system achieves outstanding efficiency and impressively low emissions. This approach represents a major step toward sustainable waste management, clean energy production, and water security. As we move toward a greener future, innovations like this will play a central role in making our world cleaner, smarter, and more resource efficient. Thank you for watching this presentation. If you found it informative, please remember to like the video, share it with others, and subscribe to the channel for more educational content like this. Your support motivates us to keep creating high-quality explanations of modern scientific and engineering advancements.